Welcome to the last section of this course. This is a hands-on section where we take everything that we learned in the last section, we apply it to real-world datasets. Let's see what we are going to do in this section. First, we will create a model to predict credit card default. We will be able to use this model and answer the question, who's going to default on the credit card payment next month? Then we will build a model to predict bankruptcy in European companies. So we will take information from the financial statements from these companies, and we will be able to predict if a company will be operating or will be bankrupt in a 5-year period. The last example will be building a spam classifier. So we will be able to take the contents of a text message, and from these contents we will be able to predict if this text message is spam or is a regular normal text message. Finally, we will discuss some further topics in predictive analytics that we didn't discuss here, and I will make some final comments about these broad topics of predictive analytics. This is the first video of this section, and here we are going to be predicting credit card default. We are going to do a lot of things in this video. First, we will talk about dummy features or one-hot encoding, which is a technique to encode the information that we have in categorical features. Then we will go to the Jupyter Notebook and start working on the dataset. We will load the credit card default dataset. We will do very quick data preparation. Then we will use the models we learned about in the last section, logistic regression, classification trees, and naive Bayes, and we will build models, we will evaluate them and compare them, and then we will pick the best one to make predictions. Okay, first, before going to the code, let's talk about dummy features. This is an example of a categorical feature that we have in the dataset that we will work with in this video. This is the education feature, and this is the encoding that we have. So 1 corresponds to graduate school, 2 corresponds to university, 3 corresponds to high school, and 4 corresponds to other levels of education. And this is how this education feature looks like in our dataset. Now, we cannot use this feature as is in scikit-learn because scikit-learn will assume that this is a numerical feature, and we know that this is actually a categorical feature. We cannot use these labels instead of the numbers because scikit-learn only accepts numbers. So the solution is to use what is called one-hot encoding or dummy features, and these are features that can take the value 1 or 0, so these are binary features. The solution would be to create one feature for every category that we have except for the last one. And these are binary features. For example, this grad school feature will have the value 1 when the education level is grad school. So as in this case and in this case, we see that we have 1, 1 and 0 otherwise. Similarly, we have this feature called university, and this will be 1 when the education level is university and 0 otherwise. So this, like in these two cases, we have an education level of university. That's why we have 1 here and 0 otherwise. And similarly, this high school feature will have the value 1 when the education level is high school or the number 3 and 0 otherwise. Now, for the last category, we actually have the information of this category because when all these 3 features are 0, then this automatically implies that the education level of this observation, or in this case of this customer, is the category 4, which corresponds with other levels of education. So this is how we encode the same information that we have in this feature in these 3 features. So if you have n categories in your categorical feature, you only need n-1 dummy features to encode the same information. Like in this case, we have 4 categories in our feature, and we only need 3 dummy features to encode the same information. Okay, so this is the technique that we will use in this case. Okay, let's go to our notebook, and here we have the credit card default dataset that we will use in this example. So these are the features that we have. Every row or every observation is a customer, and here are the columns or the features that we have. We have limit balance, which is the amount of given credit in Taiwanese dollars. We have the gender of the customer, we have the education level, and this is the encoding that we have. As I said in the presentation, we have the marital status of the customer, we have age, we have history of payment, and these features are -1 when the customer actually paid, and are positive with values of 1, 2, 3, 4, and these are the payment delay that they have in every of the months. Here we have another set of features, bill amount, and this is the amount of the bill statement for the last 6 months. So bill amount 1 for the 1 month ago, bill amount 2 will be for 2 months ago, and so on. And similarly, we have the payment amount, so how much the customer paid 1, 2, 3, or 4 months ago, and so on. So we have 6 of these features here. And finally, the target feature is default payment next month. So whether the customer defaulted in his or her payment, or if he paid. In this case, we are working in a binary classification task. So we have 2 positive values, default or pay, and I will pick the default as the positive class. So when the customer didn't pay, or when he or she defaulted, we will see a value of 1. Okay, so here I am importing the libraries we will use in this example: NumPy, Matplotlib, and Pandas. And in this cell, I am doing the data preparation. I am doing here is very simple. Basically, I am just creating the dummy features. Here I am importing the data set, and in these lines I am creating the features for the education feature. So the dummy features for the education. So here, as you can see, I am creating grad school, and these will be 1 when education is equal to 1 and 0 otherwise. University will be 1 when education is equal to 2 and 0 otherwise. And finally, high school will be 1 when education is equal to 3 and 0 otherwise. Okay, and then I will drop the education feature because I already have the information in these 3 features that I created. Similarly, instead of the feature sex, which is 1 for male and 2 for female, I will use the male feature, and this will be another dummy feature, which will be 1 when the customer is male and 0 otherwise. And similarly, I will use the same technique for married. Now, there are features that have values that are not here in the documentation, so I will make a simplified assumption here, and this is what I am doing in these lines. And when I run this, now the data has been prepared. This is a very simple data preparation, and I encourage you to do a little bit more when you are practicing with this data set. Okay, so we will build models using all features that we have. Okay, so we are importing these functions that will be useful in this process. So I am importing here from the metrics submodule in scikit-learn. I am importing accuracy score, precision score, recall score, confusion matrix, and another function that will be useful is precision recall curve, you will see in a moment. Now, since many of the features have very different scales, it is very recommended that you use some sort of scaling. In this case, we will use the robust scaler. What this object will do is to set all the variables to the same scale. So for example, the limit amount feature varies in the thousands, and for example, the age feature goes from 20 to 80, so they have very different scales. So that's why it's a very important pre-processing step to rescale the features. So let's import all these objects, and then here I am instantiating a scaler, And then I am passing the X object, which contains all the features, and I am using the fit transform to basically rescale all the features. So this operation will preserve all information, but it will rescale the features so that all the features are in the same scale. And finally, here I am, just as we did for regression, I am producing the subsets for training and testing, because we will use cross-validation for the evaluation of the models. Okay, now I have the X and Y, and here I have the training datasets and the testing datasets. Okay, this is a function that will print a nice confusion matrix, and here I am preparing a small data frame to save all the metrics for our different models. Okay, so a brief reminder, these are the three metrics that we will use: accuracy, precision, and recall. Now, in this application, these are the general definition that we gave in the last section. Now, in this context, for this application, accuracy means overall how often the model predicts correctly defaulters and non-defaulters. Precision for this application means when the model predicts default, how often is correct. And finally, recall means for this model the proportion of actual defaulters that the model will correctly predict as such. So as we said in the presentation about metrics, which metrics should I use depends on which mistake you want to avoid. So in this context, a false positive is a person who will pay and is predicted by the model as a defaulter, and a false negative is a person who will default and is predicted as a payer, as somebody who will pay. So I think my opinion in this case is that false negatives are worse. So if we want to avoid false negatives, we should go for recall for our main metric for the performance of the model. Okay, now just as we did in regression when we had a null model, here in classification we also have a null model that can be useful as a base or benchmark for how good our model must be. So in this case, the null model is the simplest model, and here we are going to predict the most common category. So in this case, most of the people paid, so the most common category is pay, or the negative category, and we are going to predict this category in our null model. Okay, so this is just a base for how well our actually more sophisticated models should perform. So they must beat this model by a lot. Okay, now let's build our first model using logistic regression. So as we said before, we have 4 basic steps in scikit-learn. First, we import the estimator object. In this case is from linear model, we import logistic regression. And in this case, the second step is to create an instance of the estimator. We will call it logistic regression, and we will not pass any hyperparameters. The only parameters that we will pass to this object will be njobs equal to -1, which is a way to say to scikit-learn to use all the cores that are available in your machine. This is for reproducibility because the optimizer inside this object will use some randomization. So if you set this to the same number, you will get the same results as I will do. Okay, so this is just for reproducibility. Once we have the estimator, we use the fit method and we pass the X training subset and the Y training subset. And then we will evaluate the model. Once the model has been trained, we will use the X test subset to make the evaluation. And we will make evaluation with 3 scores: accuracy, precision, and recall. And you pass to all of these 3 functions, you pass the same arguments, you pass the predictions, which are made here, and the true values, which are here in y underscore test. Okay, so let's run this, and here you will see the confusion matrix for the logistic regression model. Okay, now we will do the same process for classification trees. So I am passing a hyperparameter here called mean sample split, and this is the minimum number of observations that must be in a decision node to be able to split. This is to control overfitting. This is the minimum samples that must be in a leaf node, and this is also for reproducibility. So I will control overfitting with these two parameters, and then here I am training the model with xtrain and ytrain. Here I am producing the predictions in the testing data, and here I am calculating accuracy, precision, and recall. Okay, and here you will see the confusion matrix for this model. Okay, and finally, naive Bayes. The nice thing about naive Bayes is that you don't have any hyperparameters to worry about. So we import these Gaussian naive Bayes because most of the features that we work with are continuous features. So this is the recommended model that you use in these cases. Okay, so the same thing, we import the object, we instantiate the object, then we train with the training subsets, and then we make predictions on the testing dataset. Okay, so here I am recording the three metrics. Okay, and this is the confusion matrix that you have for this model. Now let's see the data frame of metrics, and here we have as percentages. So we said that the metric that we care the most about is recall. So in recall, we have logistic regression 32%, classification trees about 36%, and naive Bayes is about 55%. So let's take a look at a visualization of these metrics. And as you can see here, well, the best model when it comes to precision is logistic regression. However, since we care more about recall in this case, the best model is clearly naive Bayes. And in terms of accuracy, the best model is logistic regression, although all the models do about perform about the same. Okay, so far it looks like the naive Bayes model is the best, but this is not the full story, because as I told you in the presentations, we can modify we can adjust the values for recall and precisions by modifying the threshold, the classification threshold. So to see the relationship between these metrics, precision and recall, and the threshold, we can use this function, precision recall curve. And we pass the actual values, and we pass the predicted probabilities that we get from using this method here. Okay, so we will take a look at the relationship between precision, recall, and threshold for two models, naive Bayes and logistic regression. Okay, so here I will make a plot using the data that I got from this function. And as you can see here, we have the relationship between precision here in the x-axis and recall in the y-axis for these two models, naive Bayes and logistic regression. And as you can see, logistic regression is a little bit better than naive Bayes because for a given level of recall, let's say 0.5, you get, let's uncomment this line. Okay, so for a given level of recall, you get more precision with logistic regression. Okay, so in this space you get more performance in logistic regression. So it looks like logistic regression is actually a better model than naive Bayes. Now, so how do we do to adjust the classification threshold for logistic regression to have similar or better recall than naive Bayes? So we can do this by taking a look at the relationship between the threshold and these two metrics. So as you can see in this plot, here in the x-axis we have the classification threshold. So when the classification threshold is about 0.2, you will have a recall of about 60% and a precision of about 40 or 50%. So you can adjust the recall of this logistic regression model by adjusting the threshold, the classification threshold, to 0.2, because remember the default classification threshold is 0.5, and the results that we got here in this when we evaluated the models. These are the results when the classification threshold is 0.5, which is the default level. Now, if you adjust this classification level, you can actually change the precision and recall metrics for logistic regression. So based on this analysis, actually, logistic regression is a better model. So what we have to do here is to adjust the classification threshold to 0.2 instead of 0.5, which is the default. If we adjust this threshold for this logistic regression model, we got actually a recall of 59% and a precision of about 48%, okay? And this will be the final confusion matrix that we get from this final model. Okay, so now we can use this model, the best one, to make individual predictions, okay? So here, this function, you can pass data for a single customer, and this function will, using the model that we just built, the logistic regression model, and this classification threshold of 0.2, this model will decide if the customer will default or if the customer will pay. Okay, so here I have the data for some fictional customer, and as you can see, if I use this data in this function that I just created, the model predicts that this customer will default, okay? And this is how you use this final model to make actual predictions for customers. Okay, so this is the final step in this model that we built, to take the model and actually make individual predictions using the final trained model. Okay, excellent. I hope you liked the example. This was a hands-on, very long example, but we learned a lot from this example. We learned how to train classification models using different models, logistic regression classification trees. In naive Bayes, we learned how to evaluate them, and we were able to build a model to predict which customer will default on the credit card.